Imagine yourself in a bustling city, surrounded by towering skyscrapers, busy streets, and the constant hum of activity. Suddenly, without warning, the ground beneath your feet begins to tremble. Buildings sway ominously, the sound of glass shattering fills the air, and panic spreads as people scramble for safety. This is the terrifying reality of an earthquake, a natural disaster that can strike anywhere, at any time, and with little to no warning. Earthquakes are among the most powerful and unpredictable forces of nature. They have the potential to reshape landscapes, destroy entire cities, and leave lasting scars on communities. But to truly understand the immense power of an earthquake, we need to look beneath the surface of our planet, where these seismic events are born. At its core, an earthquake is the sudden release of energy stored within the Earth's crust. This energy has been building up over time due to the constant movement of massive, rigid plates that make up the outer layer of our planet. These plates, known as tectonic plates, are in perpetual motion, slowly drifting atop the semi-fluid mantle below. Although this movement is imperceptible to us on the surface, it generates immense stress and tension within the Earth's crust. When this stress is suddenly released, it sends shockwaves rippling through the ground, causing the Earth to shake, sometimes with devastating consequences. Chapter 2: The Tectonic Puzzle. To fully grasp the nature of earthquakes, we must first understand the concept of plate tectonics, the theory that explains how the Earth's outer shell is divided into several large and small pieces, known as tectonic plates. These plates are not fixed in place. Rather, they are constantly moving, albeit very slowly, due to the convection currents within the Earth's mantle. This movement is driven by the heat from the Earth's interior, which causes the mantle to flow in a manner similar to the boiling of water in a pot. The Earth's crust, which includes both the continents and the ocean floors, is like a jigsaw puzzle made up of these tectonic plates. There are 7 major plates, including the Pacific Plate, North American Plate, Eurasian Plate, and African Plate, among others, along with several smaller plates. These plates are constantly interacting with one another at their boundaries, leading to various geological phenomena, including earthquakes, volcanic eruptions, and the formation of mountains. The boundaries between these plates are where the action happens. Depending on the type of boundary, different types of seismic activity can occur. Convergent boundaries. Here, 2 plates collide. One plate may be forced beneath the other in a process called subduction, leading to powerful earthquakes and the formation of mountain ranges or deep ocean trenches. The Himalayas, for instance, are the result of the Indian Plate colliding with the Eurasian Plate. Divergent boundaries. At these boundaries, plates are moving away from each other, creating new crust as magma rises from the mantle to the surface. This type of boundary is often found along mid-ocean ridges, where it can cause volcanic activity and less intense earthquakes. Transform boundaries. In this scenario, plates slide past each other horizontally. The friction between the plates prevents them from sliding smoothly, leading to the buildup of stress. When this stress is released, it can result in significant earthquakes. The San Andreas Fault in California is one of the most famous transform boundaries, known for its potential to produce large earthquakes. Understanding the movement and interaction of these tectonic plates is crucial to understanding why earthquakes occur and why they are so unpredictable. These plates are in constant motion, but their movements are not smooth or continuous. Instead, they are characterized by long periods of inactivity, during which stress builds up, followed by sudden releases of energy in the form of an earthquake. Chapter 3: Fault lines, the breaking point. While tectonic plates cover the entire surface of the Earth, earthquakes do not occur uniformly across the globe. Instead, they are concentrated along specific zones of weakness known as fault lines. These fault lines are essentially fractures in the Earth's crust, where tectonic plates meet and interact. Think of fault lines as the cracks in a brittle piece of glass. Over time, as stress builds up in the Earth's crust due to the movement of tectonic plates, these cracks become the focal points for the release of that stress. When the stress along a fault line becomes too great, it overcomes the friction holding the plates together. The result is a sudden slip along the fault, releasing the accumulated energy in the form of seismic waves, what we experience as an earthquake. There are several types of fault lines, each associated with different kinds of seismic activity. Strike-slip faults. Here, the movement along the fault is primarily horizontal, with the plates sliding past each other. The San Andreas Fault is a classic example of a strike-slip fault. Earthquakes along these faults can be particularly severe, as the plates can become locked together for extended periods, allowing significant stress to build up before being released. Normal faults. In these faults, one block of crust moves downward relative to the other. This type of faulting typically occurs in regions where the Earth's crust is being pulled apart, such as at divergent boundaries. Reverse thrust faults. In reverse faults, one block of crust is pushed up and over the other. This occurs in compressional environments, such as at convergent boundaries, where plates are colliding. These faults are often associated with some of the most powerful earthquakes, such as those that occur in subduction zones. Understanding fault lines and their behavior is essential for assessing earthquake risk in different regions. By studying the history of seismic activity along these faults, scientists can identify areas where stress is likely to be building up and where future earthquakes might occur. However, predicting exactly when and where an earthquake will strike remains a significant challenge. Imagine the tension of pulling a spring until it snaps back into place. That's akin to what happens along a fault line when the stress is released. The energy released by this snap travels outward in waves, shaking the ground as it goes. This release of energy is what makes earthquakes so powerful and destructive. Chapter 4. The Ripple Effect. When an earthquake occurs, it sends out energy in the form of seismic waves. These waves travel through the Earth and cause the shaking that we feel on the surface. But not all seismic waves are the same. In fact, there are different types of waves that move in different ways and have different effects on the Earth's surface. The first type of seismic wave is the P wave, or primary wave. These are the fastest seismic waves, traveling through the Earth's interior at incredible speeds. P waves compress and expand the material they move through, similar to how sound waves travel through the air. Because they are the fastest, P waves are the first to be detected by seismographs and are often the first sign that an earthquake has occurred. Next are the S waves, or secondary waves. These waves move more slowly than P waves and travel by moving the ground up and down or side to side. Unlike P waves, S waves cannot travel through liquids, which means they are blocked by the Earth's liquid outer core. S waves tend to cause more damage than P waves because of their greater amplitude and slower speed, which results in more intense shaking. Finally, there are surface waves which travel along the Earth's surface rather than through its interior. Surface waves move more slowly than P waves and S waves, but they are often the most destructive. These waves cause the ground to roll or sway, leading to the collapse of buildings and infrastructure. Surface waves are responsible for much of the visible damage during an earthquake. Understanding these seismic waves helps scientists pinpoint the location of an earthquake and determine its strength. By analyzing the arrival times of P waves and S waves at different seismograph stations, seismologists can calculate the earthquake's epicenter, the point on the Earth's surface directly above where the earthquake occurred. Chapter 5. Measuring the magnitude. Now that we understand how seismic waves work, let's talk about how we measure the strength of an earthquake. The most commonly known scale is the Richter scale, developed in 1935 by Charles F. Richter. The Richter scale is logarithmic, meaning that each whole number increase on the scale represents a tenfold increase in the amplitude of the seismic waves and roughly 32 times more energy release. For example, a magnitude 5 earthquake is 10 times more powerful in terms of shaking than a magnitude 4, and it releases approximately 32 times more energy. This scale helps us understand the relative size of earthquakes, but it's important to note that the Richter scale is most accurate for small to medium-sized earthquakes and those that occur near the seismograph stations. For larger earthquakes, seismologists often use the moment magnitude scale, MW, which provides a more accurate measurement of the earthquake's overall size and the energy released. The moment magnitude scale considers factors such as the area of the fault that slipped, the average amount of slip, and the stiffness of the rocks involved. Measuring the magnitude of an earthquake is crucial for understanding its potential impact. The higher the magnitude, the more destructive the earthquake can be, especially if it occurs near populated areas. However, magnitude alone doesn't determine the level of destruction. Factors such as depth, distance from the epicenter, and local building codes also play significant roles. Chapter 6. Predicting the unpredictable. Despite all our advancements in seismology, predicting earthquakes remains one of the most challenging tasks in earth science. Unlike hurricanes or volcanic eruptions, which often provide some warning signs, earthquakes can strike without any noticeable precursors. This unpredictability is what makes them so dangerous. Seismologists have developed early warning systems that can provide a few seconds to minutes of warning before an earthquake hits. These systems work by detecting the faster P waves, which arrive before the more destructive S waves and surface waves. While these warnings are short, they can be enough to allow people to take cover, shut down critical infrastructure, and halt trains to prevent derailments. However, predicting the exact time, location, and magnitude of an earthquake is still beyond our reach. The Earth's crust is incredibly complex, and the factors that lead to an earthquake are numerous and not fully understood. Some researchers are exploring new methods, such as monitoring changes in the Earth's magnetic field or using machine learning to analyze seismic data, but these techniques are still in their infancy. The best defense against earthquakes is preparedness. This includes building infrastructure that can withstand seismic forces, educating the public about earthquake safety, and developing emergency response plans. While we may not be able to predict earthquakes with precision, we can mitigate their impact through preparation and resilience. Chapter 7. Building for resilience. As we enter the final act, let's explore how we can build a world that is more resilient to earthquakes. In regions prone to seismic activity, engineers and architects have developed innovative techniques to design buildings and infrastructure that can withstand the forces unleashed during an earthquake. One of the key concepts in earthquake-resistant design is flexibility. Buildings that are too rigid are more likely to crack or collapse under the stress of an earthquake. Instead, modern designs incorporate materials and structures that can absorb and dissipate seismic energy. For example, steel frames are often used because they can bend without breaking, and base isolators, giant shock absorbers placed between a building's foundation and its structure, allow the building to move independently of the ground shaking. Additionally, new construction techniques, such as using cross-bracing, shear walls, and diaphragms, help distribute the forces generated by an earthquake more evenly throughout a building, reducing the risk of catastrophic failure. Retrofitting older buildings with these technologies is also crucial, especially in regions where earthquakes are common. But it's not just about buildings. Infrastructure, such as bridges, roads, and utility lines, must also be designed with earthquakes in mind. Engineers have developed advanced materials and designs that can withstand seismic forces, ensuring that vital services remain operational even after a major earthquake. Beyond building design, community preparedness is essential for minimizing the impact of earthquakes. When an earthquake strikes, seconds can make the difference between life and death, so knowing what to do in those critical moments is vital. One of the most important steps individuals can take is to create an emergency kit. Securing your home is another crucial step. It's also important to identify safe spots in each room, such as under sturdy tables or against interior walls, where you can take cover during the shaking. Community-wide preparedness efforts, such as earthquake drills, public education campaigns, and early warning systems, can also save lives. In closing, earthquakes are a powerful reminder of the dynamic and sometimes unpredictable nature of our planet. While we cannot stop earthquakes from happening, we can take steps to protect ourselves and our communities.